All right, well, here in Chapter 3, we're going to be dealing with two topics, that is vectors. We'll just look at vectors purely from a theoretical standpoint, adding and subtracting vectors, multiplying vectors, and what have you. And then we'll also deal with two-dimensional motion, where some of those vectors will come into play. The vectors will carry over into Chapter 4 and actually the rest of the semester. We might see some 2D motion later in the semester and even into next year, but not as much. The vectors are going to be foundational for the rest of the course. So we're not going to watch Bob the Builder, unfortunately. Vectors have a magnitude and direction. We've already talked about this a little bit, but they have a magnitude and they have a direction. And scalar quantities have only a magnitude. We usually draw vectors with an arrow. And so just giving some examples of our vectors, we have the displacement is a vector quantity. We have velocity as a vector quantity. Acceleration is a vector quantity. We can also talk about generic vectors, just like about the vector A, the vector B, the vector C. And these will just be generic vectors, and we'll deal with these. We'll talk about them just having a certain number of units long, just as we're learning to deal with vectors. We represent a vector graphically, like this. We'll represent it as an arrow, and the length of the arrow will give the magnitude, while the direction of the arrow, while the direction is the direction that the arrow points. So for example, let's say that I had this vector, and let's say that this is a displacement vector. Displacement is really nice to think about vectors because the length will correspond to the magnitude of your displacement. Let's say that this vector was 2 meters long. All right, so that would say that I've covered a distance in my displacement vector. I've covered a magnitude of 2 meters. And then the direction would be given. I say, for example, this is 40 degrees. And so I would say that my vector is 2 meters at 40 degrees from the positive x-axis. And that's contained graphically in just drawing that arrow. And that would be very different, by the way, if I were to draw a vector that looked like that. That would be a different magnitude and a different direction. All right, the smaller vector in this figure has the same direction, but half the magnitude of the larger one. And actually, the picture is on the next page. I'll show you. Has the same direction, but 1/2 the magnitude of the larger vector. Oh, let's see, it's not, but I'll draw it. So I have a big vector, and then I have a vector that has 1/2 the magnitude. So if I say that this has a magnitude d, and by the way, I'm going to draw my magnitude or write my magnitude in this way, that has a magnitude d. So the bars around it basically say, I want the magnitude of this vector. I might also sometimes write it just without the arrow, and then that will represent the magnitude. So if that has a magnitude d, then I would say that this has a magnitude d over 2. But they have the same direction. Right? All right, so two vectors are equal in magnitude and direction are the same, even if they're drawn differently in the coordinate system. So for example, let's say that I have a vector that has that magnitude and that direction. That vector I can move around all that I want. So that vector and this vector are exactly the same. They have the same magnitude and direction. These vectors are the same. That vector is the same. Anytime I have the same magnitude and direction, those vectors are the same. So this whole field of vectors right here, all of these vectors are the same because they all have the same magnitude and direction. As you can move around vectors as long as you don't change their magnitude or direction. And that's what we've done here. We've just taken, say, this vector, and we move it around to different places. And that doesn't change the vector. which is the way that we draw them. As long as we don't change the magnitude or direction, then we're okay. We're going to try some graphical methods of adding vectors. This is the geometric method of adding vectors. It's called the tail to tip, or the triangular method of addition. Once you get the hang of it, when you first see it, it seems a little funny, but once you get the hang of it, it's pretty straightforward. We're going to consider two vectors, A and B. So this will be my vector A. It'll have a certain magnitude along the x-axis. And then my vector B will be this vector. So I have these two vectors, A and B. And I can find the sum of the two vectors by placing the vectors tail to tip. Or you can think of it at tip to tail. I'm going to take the head of this vector, and we're going to touch it to the tip or the tail of this vector. All right, so it's going to look like this. I'm going to take the tail. Actually, yeah, you might, I'm sorry, this is a little confusing. I'm going to take the tip of A, that is, the arrow part, and place it to the tail of B. And so I'm going to call this now, instead of tail to tip, I'm going to call it tip to tail. You really have to practice this to get the hang of it, but maybe that'll make it a little less confusing. All right, so let's see. I'm going to have my vector A. I think I drew it in green earlier. So I'll draw my vector A, and now I'll draw my vector B, And now if I want to know the vector A plus B, I'm going to draw a line from here to here. So this is going to be the vector A plus B. Notice that I do not draw a line from here to here. That is not something that I do. That is not the correct answer. All right, I have to draw the line from this point to this point. I always like to think of this in terms of displacement. Like, say, for example, I want to travel a certain distance. I travel from here, and then I travel up to here. And so my displacement, which gets me from this position up to this position, is the same as the displacement as if I were to travel from here up to there. All right, I can also subtract vectors. So let's consider A minus B. So if you are subtracting vectors, you simply switch the direction of the vector that is negative. So if I consider my two vectors, I had A and then I also had B. What if I want to know what is A minus B? So let's say that I wanted to know A minus B. Then I would draw A. Actually, let me draw that up a little bit. Space. I would draw my vector A like this. This is A. And now I'm going to draw negative B. And negative B just says it's the opposite direction of the vector B. So if I draw negative B, it's going to look like this. It's going to be the same as vector B, but in the opposite direction. So that is my A vector, and then I draw my negative B vector. And now if I want to know my A minus B, I'm going to connect these vectors in this way. So that is A minus B. Notice starting at the beginning of A and drawing to the end of B to give me A minus B. Notice that I could also, the same here is negative B minus A, or excuse me, negative B plus A. Let me show you how this is the same, and you'll see that the result is the same. So I have negative B first. So this is negative B, my vector. And then I have A, positive A. Hold on, let's see. So negative B, this is positive A. And then, so my result is going to look like this. And that's going to be negative B plus A. But notice that it is the same vector as what I had over here. Those two vectors are the same. I think that's called the commutative property of vectors. You'll get into this in Calc 3 a little bit, the different properties of vectors. All right, that is that A minus B equals negative B plus A. You can also do this for more than two vectors. So say, for example, I have vectors look like this. I'll call them A, B, and C. And then the sum of those vectors will look like this. That will be A plus B plus C. All right, we'll stop there, and I'll pick up next time. I'll post this with a